So, hello everyone. We have Anand Deopurkar again with us. He will tell about the geometric application in the study of the Fermat-type equations. Over to you, Anand. Once again, welcome.
Thank you. I just keep coming back. Okay, let me. Okay, can you see? I've written the title or something close to the title. And let me move this away. Okay. It went away. Oh, it's here. Okay, should we start?
Yeah.
Okay. So let me start with a theorem that everyone knows, the statement of, at least. I don't know the proof. It says that if the number n is at least 3 and it's a positive integer, then the equation x to the n plus y to the n equals z to the n has no integral solutions, non-zero integer solutions. This is the famous Fermat's last theorem. And as I said, I don't know how to prove this, but maybe you do, or maybe you will by the end of this year or this semester. But what I want to talk about is something related, but something more geometric. And it asks, you ask the question, okay, what's so special about this equation? It's just one equation among many. So what if I tweak it a bit? Okay, so what if I change the equation? Let's say this is star. Okay. And maybe I fiddle with the coefficients. Okay, so instead of 1x to the n, I put 2x to the n, and then 3y to the n, and I put something here, I don't know, 5z to the n. Now this has a solution, but whatever. How many solutions are there? Solve this in integers. Or maybe I also fiddle with the exponents. It's not just all n and n. Suppose I take, so more generally, I change the coefficients and I change the exponents. Okay, so let's say a x to the r, no, p. P is not a prime, okay, p is just a number. Plus b y to the q equals c z to the r. Okay, so x, y, z are variables. So a, b, c are, let's say, integers, and p, q, r are positive integers. So z. So let's say this is star, star. So this subsumes the original Fermat equation, but it's a bit more general. So you allow any exponents and any coefficients and ask, okay, how many solutions? Or are there any solutions? And I mean, this one took a couple of centuries. How many more centuries will this take? I don't know. It's hard to say exactly how many solutions there are, but what I want to discuss today is a theorem that says that there are very few solutions. So the solution set is always finite. So the main theorem for today is the theorem of pretty old theorem, Darmon and Granville, that says that under some conditions, if PQR are sufficiently big, okay, if you take something like P equal to 1, Q equal to 1, then obviously this is going to have lots of solutions. But if PQR are sufficiently big, and more precisely, that means the following. So suppose the reciprocal of P plus the reciprocal of Q plus the reciprocal of R is less than 1. Okay. So this will be true for almost all PQR, right? So the PQR that do not satisfy this condition are few. I mean, there's still infinitely many triples, but they're not that many. Then, oh, and ABC are non-zero. If you put ABC, okay, let me also write that. And ABC is not 0. Okay. So the coefficients are non-zero, and the exponents satisfy this inequality. Then star star, this equation here has only finitely many integral solutions. And solutions x, y, z in integers. And for reasons that will become clear, you have to disallow solutions that have a common factor. So let's say with GCD x, y, z equal to 1, just as you do in Fermat's last theorem. I mean, imagine if it had a solution, you could always multiply it and get a new solution. So this condition will get rid of that kind of easy way of generating infinite solutions. So GCD equal to 1. So that's the theorem. So the plan for today is to explain a proof of this theorem. So this is the plan for today. So a sketch of the proof. But I mean, this should just be treated as kind of an example of a broader point. Okay, so this is just a concrete goal for today, but somehow they're more.
When was the theorem proved?
In the mid 90s, I think, 95. So it's pretty old. Say that again?
It is Darmon-Granville paper, right?
Yeah. This is 1995, I believe. Let me check. Okay, I have
93.
93. Okay, yeah.
What, immediately after Fermat's theorem? Fermat,
Almost simultaneously he worked on it.
or at the same time,
Wait, this is 1995. Wait, when was Fermat's last theorem proven?
3 years.
Is it in the 1990s? Whilst?
1992, 93, and there was some 6-month gap.
Oh wow! I thought Fermat's last theorem was much more recent. Oh, it's been like 20, 30 years. Anyway, yeah, okay. So after Fermat's last theorem, but this is not as hard. Okay, it's like I could explain the proof of this theorem, well, modulo another big theorem, in a lecture, which I'm going to do. Okay, so this is not hard. I mean, it is hard, but it's not as hard as Fermat's last theorem. I'm not proving that there are no solutions for even a particular ABC and PQR. Okay. So what I was going to say, the broader point I want to make is that through this sketch of a proof, I will explain how geometry controls arithmetic. When it comes to solutions of algebraic equations. Okay. So let me kind of expand on this a bit before going further. So what do I mean? So you have, let's say you have a system of equations. Okay. And how do we encode a system of equations? So let's say with coefficients in the integers. Okay, so with integer coefficients. Okay. Just like star star, this is just one, but say you have a system. But this is the same as saying you have a variety or a scheme. So X, let me just say a variety over Z. Okay, that's what another way of saying a system of equations. And you're interested in, let's say, the integral or rational solutions of the system of equations. So this is just shorthand for rational valued points of X, which is the same thing as q-valued solutions of the system. So you're asking questions about the rational or integer valued solutions of X, but you have X in which you can plug in any ring or any field. In particular, you could take the complex points. And this has no arithmetic, but it has geometry. I mean, this has rich topology. This is geometry. This is an analytic object, right? This is a complex analytic manifold. And the amazing thing is that the complex analytic geometry of this has implications, or I mean, at least conjecturally, on the behavior of rational solutions. So this is the broader point I want to make, which is encoded in this slogan that geometry dictates arithmetic. So how do I highlight? And the sketch of the proof of number one. Yes?
Can you please recall if the corresponding projective algebraic curve is of genus greater than or equal to 2?
Yes, no, it's not. Okay, I'll just come to that point.
Then there is Ziegel's theorem.
Yeah.
But there is some Ziegel's theorem. So what Ziegel's theorem?
Yes.
Yeah. So how does that compare with this theorem?
Ziegel has some theorem on the finiteness of solution of integer solution of curve.
Okay, so what I'm going to reduce this to Falting's theorem about finiteness of rational points on a curve of genus 2 or higher.
I think
so you see, it's
is for I think genus bigger than 2 and integer solutions. So there are
yeah, so
many integer solutions. For
right. So
this is for rational solutions because rational
This
solutions
object
can be
X
infinite
or
level.
C may not be curve actually, right? Always.
yeah, so here, I mean, I'm saying here, I'll go into the details, but here X is not necessarily a curve. And that's why what I said here is still conjectural. But you're right that for curves, these are theorems. Well, I haven't stated anything yet except for this theorem. So, but to answer Professor Kulkarni's point, I'm not sure exactly what Ziegel's theorem is in this setting. What I'm going to reduce this to is Falting's theorem about rational points on a genus higher genus curve.
Can you explain what is the topology on X of complex numbers?
Oh, yeah. Well, just the topology in the topology inherited from the usual Euclidean topology on the complex numbers. So let's say X is an affine variety. Okay, so X is some subset of some affine space. So X of C is a subset of Cn, and the topology on X of C is just the inherited Euclidean topology. Okay.
Okay, go ahead.
Yeah. Okay. But stop me, okay? This is good. If you don't like this going into analytic geometry, you can just say kind of the algebraic geometry, okay, of xc, okay? So just the associated complex variety dictates conjecturally again the behavior of rational points of x. Okay. There are things in the chat.
Yeah, there is a problem in your presentation, Anand. It is not visible.
Mine?
Yeah, someone else complained and to me also.
Oh, what's not visible?
Board.
Oh, my board's not visible. Oh, I cannot see the board. Oh, okay. Did I stop sharing? Okay, so let me share again. Now it's visible, I hope.
Yeah, now coming. Yeah.
Okay.
Thanks.
I don't know what happened. Okay. Maybe I pressed the stop button. Okay, so let me keep going. Okay. I'm going to repeat some of what I said, so if you miss something, it's fine. Okay. So let me explain this slogan, conjectural slogan, that geometry dictates arithmetic. And what I'm going to say is are theorems in the dimension 1 case, okay? So let's take the case of curves. Okay. So x, let's say over Q, is a smooth projective curve. Okay. And we ask about x of Q. The set of rational points on x, rational solutions to the defining equations of x. And there are 3 cases. So the easiest case is, and the cases depend on the properties of x over the complex numbers. Okay? So the first case is if the genus of x, by which I mean the genus of the Riemann surface associated to x, okay? Just the topological number of holes. Okay, if the genus of x is 0, well, then there are 2 possibilities. Then either, so for example, this curve here, the Fermat curve with n equal to 2, okay, this is a curve of genus 0. I have 2 x's, but I hope they don't cause confusion. Then there are 2 cases, that then either x has a rational point, like this one, it has a rational point. And if it has a rational point, then x is actually isomorphic to P1 over Q. Okay. And as a result, it has infinitely many rational points, because P1 has infinitely many rational points. So we know if I dehomogenize this, that's just a circle, right? And it has a rational point, this one, for example. And then I can use just a rational parameterization, let's say by lines through this point, to get a whole bunch of an infinite set. In fact, all of them, all of the rational points on this curve. And that holds in general. that once you find one rational point, you can just produce all of them by producing an isomorphism with P1. Okay? Or it may happen that X has no, so either is A, is B, X has no rational points. Well, then maybe you're unlucky, but it'll always have a point over a quadratic extension. So it always has a point over an extension of degree 2. Okay? And then, well, if you just extend your field to K, then X is isomorphic to P1 over that field. Then X K is isomorphic to P1K. And as a result, has infinitely many K points. So the term used is that so in any case, A or B, so A or B, there exists a finite extension K of Q such that the set of K points is infinite. So maybe the extension is Q, or maybe it's some finite degree 2 extension, but potentially, so after a finite extension of the base field, you always get infinitely many rational points. Okay, so the term used is that rational points on X, which is of genus 0, okay, these are potentially infinite. So the word potentially here always is going to mean that possibly after a finite base extension. Okay. So if you have a rational curve, a genus 0 curve, then the rational points on X are up to a finite extension of base field. You always have infinitely many rational points. So this is the case number 1. Okay. Case number 2 is if the genus of X is 1. And here the story is also similar. Okay, so here, so what does this mean? So it could happen that X has no rational point, but you could always pick a finite extension and get a rational point. So after a finite extension, get a point. Okay, and then you can make this point the origin and put a group structure on X. So then you get an elliptic curve. Well, it may happen that the elliptic curve, the set of rational points is finite. Okay? But you can always make another base extension, and so that you get a point of infinite order. Okay? So maybe after you get infinitely many points. Okay? So in this case also, you have a potentially dense, potentially infinite set. Of rational points. Okay. The third case is distinctly different. Okay, so this is the genus of X is 2 or higher. Okay. So this is kind of, I'll call it the hyperbolic case. This is the elliptic case, and maybe the first one was the spherical one. Okay, Riemann sphere. Okay. And in
Sorry,
the
a
hyperbolic,
question.
yeah.
Why after a finite extension for elliptic curves for genus 1,
Yes.
after finite extension, we can give a point of infinite order?
Yeah, it's not obvious, okay?
Uh-huh.
Because I mean, you can imagine there's nothing. Sure, if your base field was like the complex numbers or any uncountable field, then obviously you have a point of infinite order because the points of finite order are countable. But Q bar is also countable, right?
Yeah.
So it's not obvious, okay, that you can get a point of infinite order. And I mean, just in the 5 minutes when the technical problem was being resolved, I was thinking about this, and I don't have a proof in my head right now, okay? So, but I know it's true. Okay? I just leave it as an exercise. It's not obvious, okay?
Yeah,
That
so
you
this is not
can, okay?
trivial
No, it's not
implication.
immediate. It's not immediate, okay?
Yeah, sure.
But
Thank you.
I don't think it should be that hard, okay? If you know enough about elliptic curves, probably do. But it's yeah. So this is. I'll just leave it, okay? Because I don't have an argument in my head right now.
Okay, thanks.
Yeah, but it's true. All right, and the next case is exactly the opposite. So here, so there's a theorem. So this is a theorem of Pointings. When was this proven? Who knows? Surely before Fermat's last theorem. Yeah.
Yeah, I think 1977 or 75 something.
75. Okay, okay.
75,
So
77. Before
yeah?
80, just before 80.
Just before 80, yeah. So definitely before Fermat's last theorem. And what does this say? So it's a x over q, a curve of genus g greater or equal to 2. Okay, smooth, projective. Then for any finite extension k over q, the group of the set of rational points is finite. Okay. So even after you allow yourself the freedom of making a base field extension, you don't get infinitely many rational points. Okay. So here's the summary. Okay. And 3 cases: spherical, elliptic, and hyperbolic. And I mean, I stated it in terms of the genus, but let me state it in terms of the degree of the canonical bundle, okay? Because that's what generalizes, or I mean, is expected to generalize. Okay? So spherical means the degree of the canonical bundle is negative.
Maybe correct that as in 1983. Yeah.
83? Okay. Maybe it was on the archive in 75 and published in it. I don't know. There was probably no archive then. Yeah, so the degree of the canonical bundle for a genus 0 curve is -2, which is negative. The degree of the canonical bundle for the elliptic curve is 0. And for hyperbolic curve, it's positive. Okay? And it has implications on rational points. In the first 2 cases, you get potentially, well, I'll write potentially dense, okay? Because that's what's expected to generalize. But these are curves, so dense here means in the Zariski topology. And for curves, a dense is the same as infinite. Okay? So the only closed subsets, strict closed subsets are the finite sets. So here, in the first 2 cases, we have a potential density. And here we have not potentially dense. Okay? And okay, so this is a conjecture that a similar story holds in higher dimensions. Conjecture. This is where it's attributed to Bombieri and Lang. And I won't state it precisely. Okay, but so let's say x over q is let me put smooth projective variety. Okay, then so what's the analog of spherical? So spherical should mean, in some sense, it's roughly, it means close to being a rational variety. Okay, so it's close to a projective space. Let's say it's a dimension n. Okay, close to projective space. So it may be birational to projective space. Okay, in that case, obviously it has infinitely many points. Or it could have just a dominant map from projective space, then it also has infinitely many points. It could be something even weaker, sometimes called a Fano variety. So for example, could be Fano, which is an analog of the negativity of the canonical bundle. So here it means that the canonical bundle is anti-ample. Okay. In these cases, we expect that conjecturally, I think this conjecture is Campana's conjecture. Conjecturally, the set of rational points. So there should exist a finite field extension so that the rational points are Zariski dense. Okay, so potentially dense set of rational points. So if your variety is close to projective space, defined appropriately, then you expect it to have lots of rational points. And the other extreme, the hyperbolic, is what's called a variety of general type. And that's the analog of this positivity of the canonical bundle. So this means that the canonical bundle is close to being ample. Okay, so let me write ample here. Or there's a word called big, which is not quite ample, but close to it. But that's the analog of the positivity here. Okay? So this was the analog of the negativity here. Then there's a conjecture of Lang-Bombieri that the rational points are not potentially dense. In dimension 1, this just reduces to Falking's theorem, which is a theorem. But in no higher dimension is this a theorem. In dimension 2, we don't know it, and higher dimensions, we don't know it. It's a complete mystery. Okay, what about the intermediate cases? Well, it's complicated. Okay, and I might send you. I will send you, Devendra, some notes that I wrote for this talk, in which I have references, if you want to read about like what's expected in the intermediate range. Okay, what does this have to do with Fermat-like equations? So let's go back to actual math, which was this solving this equation. Okay. Okay, so this is a variety, right? So this is, let's call this the solution set of this in A3. Let's call this X. Okay, so this is a variety defined over the integers. Okay. Looks like a surface, right? It's three variables and one equation. which is a problem because I just said that this kind of geometry implying arithmetic is only conjectural, and the only case where it's known is the case of curves, right? And X doesn't look like a curve, it's a surface. Okay. But I also said that this is a theorem, that this is finitely many points. So what's going on? Well, X is a surface, but it's secretly a curve. Okay. Why is it secretly a curve? Well, X has an action of the multiplicative group. So this is not quite homogeneous, but it's quasi-homogeneous. So this is just the multiplicative group. And what you can do is you can just choose your scaling parameters cleverly so that they match up. Yeah.
The surface may not be smooth.
Yeah. Of course. Yes. Yeah. It's almost definitely have to throw away the origin. I mean, it's definitely not smooth at the origin. Okay. I'm going to be a bit. What should I say? Careless here. And when I say X, you should just imagine X minus the origin. There's also because 0, 0, 0, that's the solution. Great. Throw it away. Okay. Even then, it may not be smooth, I guess. Yeah.
Is your question only up to birational type?
Yeah, it's only up to birational type. Yes.
So you're dealing only with function fields, only with the meromorphic function field of the variety.
Yes, only with the meromorphic function field. Okay. Let me erase smooth. So projective variety. Then the conjecture is expected to hold. I mean, this is a birational type. I mean, being of general type is a birational condition. So
yeah. Am I correct that your question, whatever variety,
yes,
XQ is finite or not finite?
Yes.
That just depends on the birational type?
Let me not say anything that precise because that will include the things in here also, right? Yeah. I'm also not saying anything about finite versus infinite. I'm only saying about is it Zariski dense or is it not Zariski dense? Okay. And in this case, at least, the conjecture is that having a Zariski dense subset of rational points is a birational property. Which, I mean, makes sense. See, if two varieties are birational, right? Mm. And one has a dense set of rational points, well, the other one, okay, it may not have a dense set of rational points, but after a finite, so there's some birational map, okay? It's defined over maybe not the base field, but some field extension. And the other variety will have a dense set of rational points over a finite field extension. So having a potentially dense set of rational points is a birational property. Right?
Because this birational or rational, that's defined over algebraic closure. In the first
yeah. This is defined over the algebraic closure, yes.
Yeah. And now you're asking questions over subfields of the closure. Yeah.
Yes. Okay. By the way, if you were confused by what I said earlier, you can tune back in because I'm not going to use any of these conjectures. I'm just going to prove it like by hand. Okay, so this is not going to understanding these conjectures is not a prerequisite for what's coming next. Okay, so if you got lost because I was bad at explaining, just ignore it and come back. Okay. So this is some variety, right? X, and it has an action of the multiplicative group. If P, Q, R are equal, it's obvious what the action is. You just scale X and Y and Z by the same T. But even otherwise, you can be clever, and so let T act on X, Y, Z by multiplying T by, let's say, QR, okay, Y by PR, and Z by PQ, and that works. Correct? That leaves this invariant, this equation. So this has an action of the multiplicative group. Okay. And what we should be looking at, so this is also the reason why there's not much difference between, let's say, rational solutions and integer solutions, because if you have a rational solution, you could just scale it by a huge T and make it integral. So what we should be looking at are not integer solutions on the nose or rational solutions on the nose, but rational solutions up to this kind of scaling action, which we all understand when P is equal to Q is equal to R, but it's slightly less obvious when these are distinct. Okay, so what we should be looking at is, look, not at X itself, okay, but at the quotient, X modulo this action of GM. Okay, and remember, X was a surface, GM is one dimensional, so this should be a curve. Okay. Again, as I said, when I take the quotient, I surely want to throw away the origin. Okay. So maybe let me just define X as the complement of the origin. Okay. So, right. Okay. Now, what is this quotient? So what's this quotient? So it could be, it is a bit tricky. It depends on what P, Q, R are, right? But the easiest case, let's say for simplicity, let's assume that P, Q, R are pairwise coprime. Okay. This is kind of maximally away from the homogeneous situation. Okay. I'll relax this assumption soon, but just to see what this quotient is, let me assume that P, Q, R are pairwise coprime, and then it's easy to see what the quotient is. Then the quotient is just P1. Remember, X does not include the origin. Okay, so X mod GM is P1, and what's the map? So the quotient map is given by X, Y, Z goes to AX to the B, Y to the Q, C, Z to the R. Okay, this looks like a point not of P1 but of P2, which is true. It lies in P2. But this P1 is the vanishing set of X plus Y minus Z in P2. So the fibers of this map are exactly the GM orbits, at least when PQR are pairwise coprime. Okay, so the quotient is P1, realized via this map. That's not good. Why is that not good? Because I asserted that it has, this X is supposed to have very few rational points, right? Modulo this group action. But if modulo this group action the variety I'm getting is P1, then P1 has infinitely many rational points. So seems to contradict. So this seems odd, kind of at odds with the theorem that with the main theorem with the Darmon and Granville. And also the PQR condition never showed up. I mean, this condition, that's not what I stated. It was something about the size of PQR, right? So what's happening? So you have it's not P1. This is the quotient by GM. What's happening is that this is not the right quotient. Okay. So this is not how you should think about the quotient. Because what's the point? The point is that the GM action, the action of GM on X, is not a free action. Okay. So this is not a GM, this is not a principal homogeneous space with fiber GM. Okay. There are certain orbits that have non-trivial stabilizers, and there are precisely 3 orbits. So there are 3 orbits, okay, that have non-trivial stabilizers. And the first is the one corresponding to x equal to 0. Okay? When x is equal to 0, the y and z lie in one orbit. Okay? So this orbit has stabilizer mu p, the pth roots of unity. Is that right? Yeah. Okay. So the pth roots of unity will act trivially on y and z, and only those. Okay. Y equal to 0 has stabilizer mu r, right? And z equal to 0 has stabilizer q mu r. Okay? And the other point, so away from these 3 special orbits, the action is free, and the quotient is actually p1 minus 3 points. But at these 3 points, you have extra stabilizers. Okay? So what's a better way to think of the quotient? So you should think of the quotient as being not a P1, but some P, which is an orbifold, Lee-Mumford stack, however you want to say it, but its underlying space is P1. Okay, so it's like a P1, but it has 3 points which have non-trivial stabilizers. So there's 3 points with stabilizers mu p, mu r. I've skipped q for some reason always, and mu r. Okay? So that's an honest, a more honest representation of what the quotient looks like. Okay? It's an orbifold P1 with 3 points with non-trivial stabilizers. The rest of the points have trivial stabilizers. So that's the quotient. Okay? That's P. And then we should go back and apply our spherical elliptic hyperbolic heuristic. Okay? So what should P count as? Should it be elliptic, hyperbolic, or spherical? Well, how do we tell? Well, we just look at the degree of the canonical bundle. And what's the degree of the canonical bundle? Well, if you compute the degree of the canonical bundle correctly, use in the orbifold sense, then this is a fraction, but it's this.
I see.
So great, beautiful. So expect what we should expect. Well, this is not a theorem. This does not follow from Faltings, because Faltings did not prove the theorem for orbifolds. He proved it for curves. Okay. So, but I mean, we should expect the same thing. We should expect that when this is positive, okay, when this is positive, we have very few rational points. Okay? Which is exactly what the theorem claimed, okay? Of Darmon and Granville. Okay? And maybe this also suggests a way to prove it, and Darmon will exactly follow. They prove this expectation by reducing. I mean, where does this expectation come from? It came from Faltings's theorem that this is exactly what happens when you have an honest curve and not an orbifold. Okay, so they prove this by reducing it to Faltings. Okay. And I believe I do have 10 minutes, right? So
Maybe you can take 10 more minutes because there was delay.
Yeah, that's what I thought. So let me take 10 more minutes. But let me also say this, that if you want to go away from this talk, I mean, this is the point that you should take to heart, okay? That the real quotient is this orbifold curve, which has positive canonical exactly when this 1 over p plus 1 over q plus 1 over r condition holds, and that is the reason why we have finiteness of rational points. Okay? That's the moral of the story. Okay? So here are the details. Okay? So I mean sketch. So what the idea is to, okay, this p is an orbifold, right? So we don't like orbifolds, we like curves. So I'm going to kind of approximate p by an honest curve, okay? So what that means is the following. So this is p1. Let me put these points at 0, 1, and infinity. There's like 3 points on p1. I can do anything. And let me choose a curve y with a map to p1, which has the following ramification profile. Okay, it needs to have all ramification p over 0. Okay. So the monodromy around 0. So this is happening over C. Okay, so the monodromy around 0 is like a product of p cycles. The monodromy around 1 is a product of q cycles. Okay. And the monodromy around infinity is a product of r cycles, and there is nothing else. There's no other ramifications at all else. Okay. So let y to p1 be a cover like this. Okay. It's not obvious now that such a thing exists. Okay. So obvious that it exists, but it's not that hard either. You just have to kind of solve some equation in a symmetry group, right? That a permutation that looks like this times a permutation that looks like this equals a permutation that looks like this. If you solve it, then you have it. Or you can be a bit clever and do something with triangle groups, which is what he does, but it does. Okay, maybe this can be another exercise. Prove that such a thing exists. Okay, great. So it exists, but this is over C. But then we have a theorem, which I talked about a few months ago by Belli, that says that this can actually be defined over a number field. Okay, so y to p1 can be defined, maybe not over q, over a number field. Okay, so, okay. And so here's kind of what's going under the hood. So when we insist that y has a ramification exactly like this over p1, that's the same as saying that y admits a map to this orbifold p, and this is actually a covering space. Okay. So you should, in that sense, y is kind of very close to this orbifold. You should really think of this as just an approximation, like an honest curve approximation of P. Okay? But I mean, this you don't have to write in the paper. They don't write this in the paper, but this is what they are thinking, I think. But okay, so the y to P is this curve, and then you just compute the genus of y, and sure enough, it's at least 2 if this condition is satisfied. Okay, and that also you see why it has to be true, because this is an étale cover, right? So the Euler characteristic of y is just going to be a multiple of the Euler characteristic of P, or the degree of the canon. Yeah.
That is less than 1 over P plus 1 over P.
Yeah, less than 1, sorry. So the degree of the canonical of y is going to be a multiple of the degree of the canonical of P, and if the degree is positive, the degree here is positive, and that translates to genus greater or equal to 2. Okay? So this is, but you could just do it honestly using Riemann-Hurwitz. Okay. If you don't want to use this mumbo jumbo. Okay. And what's the key proposition is that, so here, this is what's happening. So you have X mapping to P1, okay? And this is just the quotient by GM map, okay? This is the bad quotient, ignoring the orbifoldness. But to remedy that, we've taken this curve Y to P1, okay? So the key idea is the following, and what we're interested is in, let's say, rational points of X, okay? Or integer points, it's not the same. Yeah.
I think instead of this explicit calculation,
Yeah.
can you not take y to be some even a Galois curve? Galois?
Yeah, you can. Yeah, you can take a Galois. In fact, you can do it with a Galois cover. Yes.
And Bailey would still apply.
What will apply?
Bailey's theorem.
Yeah, Bailey will still apply. Yes. Yeah.
That is defined over some number field.
Yes, it applies. The only thing that Bailey needs is that the ramification is concentrated in 3 points.
So that explicit calculation that is there, such a y exists with that 3.
Yeah, but you still have to, I mean, prove that there is such a Galois cover, right?
Yeah, I think Galois cover needs some extra kind of subgroup of triangle.
It's a triangle group, and so
Not
Yeah. That's right. There are
normal subgroups of the triangle group correspond to Galois cover.
that's right. And in fact, you can do it with a normal subgroup. So you can do it with a Galois cover. But for the argument, I mean, and in the paper, they do construct a Galois cover. But what's essential is not that it's Galois, but it has kind of uniform ramification. That's what's essential.
you need the uniform ramification.
Yeah, you need the uniform ramification. Yes, that's the key point. Yeah.
I see.
Okay. So now what's the key? So let's say you have X, Y, Z. Let's say it's a primitive
That's clever.
integral solution. A primitive just means GCD equal to 1 of X, okay? So this gives rise to a rational solution. I mean, let me even say, so this, okay, this bottom is only defined over K, right? So this actually gives you a K-valued point of P1, just the image. I mean, specifically, it's the point AX to the P, B, Y to the Q, C, Z to the R, okay? But there are lots of K-valued points of P1 because it's P1, right? But the key idea is that there is one extension. There is one extension, L of K, such that a point of this form, let me call it star. Okay? A point, a k point star of this form of P1 is the image of an L point of Y. Okay? It's even stronger. Okay? Sorry, pressed it too many times. Such that, in fact, if you take, this is, let's say pi. In fact, if you take pre-image of star, okay, so this star is a point of P1, this pre-image lies in Q, so its points are L points. So, and you need only one extension. So if you take points of P1, k points of P1, which arise from points of X via this map, then their pre-image in Y is actually an L point, where L is some fixed finite extension of K. Okay. And as a consequence, so I mean, it's kind of this, okay, what's the slogan? Is that k points of P1 that arise from X, okay, these are the same as, well, L points of Y, okay, where L is some fixed extension of K. And well, now you use Faltings. So Faltings implies that Y of L is finite. Okay. Because Y is a higher genus curve, L is a fixed field, right? I mean, it's a fixed extension of Q. So Y of L is finite. So the points of P1, the k points of P1 that arise from X by this map are finitely many. Okay. And as a result, you can prove that points of X primitive with no GCD are finitely many. So that the key is not to look at all points of P1, but points of P1 which should count as points of that orbifold, okay? Meaning coming from X, and those up to a finite extension are points of a higher genus curve. Okay. Well, how do you prove this key? Well, read my notes or the paper, because I think I'm
Yeah, it is getting maybe.
out of time, so I'll start.
No, maybe you can explain that your paper you cited in your abstract.
Oh yeah, okay, so okay, here are the references.
You wanted to talk about Harris and Mazur's paper, maybe.
Oh yeah,
5 minutes time.
should I? Okay, maybe. All right. Okay. Let me just. Okay. Yeah, I did not make even a mention of that. So going back to this broader point, there was this conjecture of Lang, which was in the spirit Lang-Bombieri, that says that a variety of general type implies there are few rational points, right?
Is this proved?
No. No one expects that we're anywhere close to this. This is only proved in dimension 1, which is Faltings theorem. Okay, it's only proved in dimension. I mean, only proved only in dimension 1. Yeah.
This
But now, yeah.
specific Fermat-like equation that could
Yeah.
be replaced by some more general equations.
Yes. Wait, let me.
Rational coefficients, but not homogeneous.
Yeah.
And then you can use your CM trick
Yeah.
and get that as a covering on P1,
Yeah.
and then the same argument would apply, no?
Just a second. What argument would apply?
No, instead of saying just ax to the p plus by to the cube equals cz to the r,
Yeah.
you could throw in some mixed terms also.
Yes. Yes.
And perhaps
Yes.
some similar argument may work.
I mean, if it has, well, okay, if it has some quasi-homogeneity, if it has a GM action that reduces it into a curve, then you would be able to use something like faultings to get some finiteness. But if it's honest, yeah, but if it's honestly a surface, right? If it's then well, you can do something else, but you can't use this because it's conjecture. I mean, you can, but you'll get a conditional result. Okay, but what I wanted to just maybe state now is that this has strong implications on somehow the behavior of rational points in families. So let me state a theorem. This is a theorem of Caporaso, Joe-Harris, and Mazur, well, which is conditional on Lang-Bombieri. Okay, so assume Bombieri-Lang holds in all dimensions. Okay, then there exists a constant. Okay, and fix a number field K and a genus G. Then there exists a constant, let's say n, which is a function of G and K. So the genus and the number field, such that all genus G curves, such that for all genus G curves, x defined over K, the number of K rational points of x is less than n. Okay. So faultings says that for any given curve of genus G over K, the number of K rational points is finite. This is a much more stronger, something much stronger. It gives a uniform bound. It says that even if you vary the genus G curve over all possible genus G curves defined over that field, the number of rational points is bounded above. Okay, so this so I mean, for example, if you take this Fermat equation is one equation of degree n, right? This is homogeneous. So if you take like any homogeneous equation of degree n, I don't know, yeah, just put anything. Yeah, I mean, there's so many terms you could put in, okay? And all of these have, there will be a uniform bound on the set of Q solutions. So there exists a uniform bound. Well, assuming Bombieri-Lang. So this was a paper. This is, I think this is also 1997. So if you want to read that, it's a beautiful geometric argument. With that, I don't want to say anything about the proof because I'm already over time. Let me stop. Yeah.
It's for you, maybe midnight occurring.
Yeah, it is midnight. Yes.
Thanks. Let's thank the Anand for his wonderful talk.
Bye bye.
Yeah. Okay, thank you. I just mentioned this theorem.
Do we have any time for questions or maybe not?
I have only mentioned this theorem,
Yes.
Ziegler's theorem, in the chat box. It is
Yeah.
for curves, but here we are doing a surface. So that is basically
Yes.
the difference.
Yes, that's
Ziegler's theorem is for surface for curves only. Curves of
That's
0
right.
e bigger than
Yeah.
0, then
Yes.
finitely many integer points.
Yes.
So here one is considering a surface basically. Therefore,
Yes.
it's a new result actually. That is the difference.
That's right. Yeah.
Yeah. But maybe there are, that was I think the question asked by Professor Kulkarni, that are there any other surfaces for which such finitely many solutions, integer solutions, such things are known. That is also one thing.
That's a good point.
This is basically
Probably,
triangle.
but I don't know.
Yeah, but this is specific. We are using triangle, that this triangle group idea.
Yeah.
In this thing,
Yeah.
this theorem is unique to this triangle group thing.
That's right.
But maybe there are using some other ideas. There may be some finiteness theorems like this, but one doesn't know. I mean, this itself is surprising because I think after this Ziegel's theorem, I don't think anything much is known, any general result about
Right.
finitely many integer points. But this itself is a totally new result, and for higher, I mean, one more variable. So 3 variables.
Yes.
One is having
Yes.
this result.
Yes.
So this is, I think, open for more variables and any other surfaces coming out of some different ideas.
Right.
Yeah, right.
Does anyone among the audience have a quick question? If
Sir,
not,
an undergraduate here.
yeah, tell.
Hello.
Sir, can you recommend a book to as a prerequisite of understanding for someone who is getting into algebraic number theory and has just started with elliptic curves? Any good recommendations for book?
His first
Ireland
year
and
student.
Rosen. I think Ireland and Rosen is one good book for algebraic number theory and interesting results in different directions. So Ireland and Rosen, I think, is one book. But elliptic curves, Silverman and Tate, that is a good book.
I think that's a classic. Yes. Silverman Tate.
Silverman and Tate, you can see elliptic curve basically.
If you want to understand Fermat-like theorem while reading number theory, use the Marcus book.
That is slightly more advanced. We can see that Marcus book is certainly.
But it asks you to solve a lot many problems.
Marcus certainly.
Okay, Anand, thanks.
Bye bye.
Thank you.
Thank you.
Bye. Yes.
Happy Sankranti.
Yes.
Yes, you too.
Okay, so we close it.
Close it. Yes.